The purpose of this video is to show you how to set up various types of financial word problems in the TVM Solver on your TI-83 or TI-84 calculator. To get to the menu, you want to click on the Apps button, take the first option, which should be Finance, and the first option after that is the TVM Solver. Within the TVM Solver menu, we have all these various variables. N is the total number of payment periods. I is the annual interest rate entered as a percent. So for example, 4% should be entered as 4, not 0.04. PV is the present value. That's the amount in the account at the beginning of the problem. Payment is the ongoing deposits or withdrawals that are occurring in each payment period throughout the problem. FV is the future value or the amount in the account at the end of the problem. P per Y is payment periods per year. C per Y is compound periods per year. And we also want to indicate if ongoing payments are occurring at the end or the beginning of each of the payment periods. Let's look at an example of just compounding interest. Suppose that Sarah has invested $5,000 in an account that's earning 6% compounded quarterly. So the interest rate is 6. The compounding is quarterly. And N is not 2 here, it's 2 times 4. 2 years times 4 quarters per year equals 8 compounding periods total. The present value is the amount of money at the beginning of the problem. In this case, that's a $5,000. In fact, it's a negative $5,000. Now, why is it negative? Because Sarah is taking her money out of her pocket and leaving it with the bank. So from Sarah's point of view, this is a negative transaction. She's leaving the money behind in a savings account. So I have a negative $5,000 for present value. Sarah is walking away and not coming back until the end of the problem. So there are no deposits or withdrawals that are occurring. There are no ongoing payments. So that would be a 0. And then one of these remains to be determined. That's what we want to find in this problem, is the future value. And you want to put your cursor on the future value line and press alpha enter. Alpha solve will cause the TVM solver to find the missing variable, find the value that fits where your cursor is at, that fits all the other numbers that you've entered. And in this case, if I alpha solve on future value, the result we get is this 5, 6, 32, 46. Notice that it's positive, which makes sense. The money is coming out of the bank back to Sarah, and it's more than 5,000, which is good because we started with 5,000 and that was supposed to earn some interest. In this example, we want to determine what must be invested today in order to obtain a certain future value. Okay, so the present value is the unknown. That's the thing I need to solve for. There are no deposits or withdrawals happening, so the payment is 0. I see there the interest rate is 5, and the future value is 80,000. Now, is it positive 80,000 or negative 80,000? It's positive because Susan plans to receive this money in the future from her investments. So a positive 80,000 for future value. The compounding is monthly, so I'm going to put 12s in down here. And N is 10 years times 12 months per year, or 120 months total. That's the number of compounding periods. We alpha solve for present value, and you see what we get here, $48,572.88. It's negative, that's correct, because this is the amount that would need to be deposited at the beginning of the 10 years in order to end up with 80,000. And it's less than 80,000, which also makes sense because this money has 10 years of time in which to grow and accumulate interest. This question asks about what interest rate would be necessary to go from 50,000 to 100,000 in 15 years. Okay, so the interest rate is the unknown. That's what we're going to alpha solve for. The present value is what we start with, and we're starting by investing by depositing $50,000. So I got a negative $50,000 here. We walk away from the account, no deposits, no withdrawals. So the payment is 0. And then the future value is how long does it take for the money to double? So we're expecting $100,000 to come back. Now in terms of how the compounding works in this problem, it's quarterly. So these are 4s, and 15 years times 4 quarters per year equals 60 total compounding periods. And when we alpha solve, you see that we get 4.647776, etc. Here we have an annuity, and the difference in this problem is that Will is making this payment each and every year. So this is not a one-time investment. This is an ongoing deposit that's growing over time. The interest rate is 6%. The interest is compounded annually. And Will is also making annual payments. So there's one payment per year, and there's also one compound per year. And these payments are made at the end of each payment period. And what are these payments? The payments are $3,000. And that money is going from Will into the bank. So let's make that a negative $3,000. And this is going to occur over the course of 5 years. N is 5. What's the present value? Well, it's actually 0. You might be tempted to think it's 3,000, but Will is starting with nothing in his account, and there's nothing in the account until the end of the first year when he makes the first payment. Now you could imagine a scenario where maybe Will starts with, I don't know, $20,000 in his account, and then he continues to add $3,000 each year. And if that was the case, then our present value would be a negative $20,000. But in this case, there's nothing in the account at the beginning, so I want to start with a present value of 0. Payments are negative $3,000, and now I'm alpha solving for a future value. And when I do that, the calculator gives me an answer just under $17,000. It's positive, which is good. This is an investment that's supposed to be growing. And if I deposit $3,000 a year for 5 years, that's $15,000. So we'd expect this to be a little bit more than $15,000, and that's what we got. Okay, another example of investing in an annuity. The interest rate in this problem is 8%. And everything in this problem is occurring quarterly. The payments are quarterly, the compounding is quarterly, and the payments are made at the end of each payment period. And this is ongoing for 30 years, so N is 30 times 4 for 4 quarters per year. There's going to be a total of 120 quarters in this problem. Mark is starting with $0 in his retirement account. At the beginning of this problem, there's nothing in the account. What gets added to the account each month? Well, Mark adds $1,000, but his employer actually matches it. So a little tricky here. We're actually going to add $2,000 into this account each month. And it's negative because the money is being deposited into this account. So for 30 years, deposits of $2,000 each month leads to a future value of just under $1 million. Not too bad, especially if you think about how much was actually deposited. So if we deposit $2,000 every month, and we do that, I'm sorry, not every month, every quarter, and we do that for 30 years, so we make 120 deposits of $2,000. That means the total amount deposited was only $240,000. And in fact, what Mark deposited is actually half of that. Mark has only invested a total of $120,000 out of his paychecks. And notice that in the course of 30 years, his retirement account is close to $1 million. And that's the power of compounding interest, especially when you have a nice big fat interest rate like 8%, which is what we had in this problem. This problem's a little bit different than the last example because we're not investing money into a retirement account. Kate is retiring. She's imagining that she's already got this fund built up and now she's drawing money out of it each month. So we're not depositing savings into a retirement account. We're withdrawing money from our nest egg to live on. All right, how does that change things? Well, the interest rate in this problem is given as 6%. The payments are to be received every month. The 6% interest rate is compounded every month. The payments are made at the end of each month. How many payments are there? Well, Kate is hoping that this account will last for 20 years, and she wants a monthly payment. So 20 times 12 is 240 total months. In this problem, the present value is what we're trying to find. I don't know how much money Kate needs at the beginning of this scenario. That's what we're looking for. We know that she's going to draw out $3,000 every month. This is positive because these are withdrawals. This is money that Kate is receiving. And the future value may be a little unclear to you, but we're imagining that we start with a large amount of money. We draw out $3,000 every month, and we're hoping that this will last for 20 years, meaning that the money runs out at the end of 20 years. So we've got a future value of 0. And when we alpha solve for present value, the calculator determines that we would initially need just over $400,000 for this money to last 20 years. Let's change this problem ever so slightly. So a lot of the numbers are still the same. 20 years, 6%, $3,000 per month until it runs out. The payments are coming at the end of every month. But here's the change. The interest is not compounded monthly. The interest is compounded annually. So the compounding periods are different than the payment periods. Kate is getting $3,000 each month, so P per Y is still 12. But in this example, C per Y, the number of compounding periods per year is 1 because the compounding is annual. So this is not an ordinary type annuity. And now when I alpha solve, you see here that Kate is going to need slightly more money than she did before, which makes sense because if the money's not being compounded as often, we need to start with more money in the account at the beginning. What about loans? Borrowing money for a mortgage. The interest rate is 4.98%. The bank has just given Mark and Kathy a house, so the problem starts out with Mark and Kathy just being handed $210,000. This is positive because it's being received by the individuals. And the payments are to be made monthly. The interest is compounded monthly on the outstanding balance, and the payments are due at the end of the month. How many payments are there? This is a 30-year mortgage with monthly payments, and 30 times 12 is 360 payments. So Mark and Kathy are anticipating paying this off in 30 years. So that's the future value of 0, completely debt-free. And now we alpha solve for monthly payments. And in this case, the payments are $1,124.76.